Welcome to Talkin Science Interviews, the podcast where we dive into science and space. As the final instalment of 2021, it's time for a clip show and a countdown of some of our guests from the year in absolutely no particular order.
This is Trekzone's Talkin Science.
And Professor David Flannery is beaming in for a Trekzone conversation right now. David, thanks so much for your time this morning.
G'day, thanks for having me.
Now, Hayabusa is coming, we're gearing up to this coverage on Sunday of the sample returning to Earth. It's going to be landing in Woomera. OSIRIS-REx is coming as well. That tagged asteroid Bennu a couple of months ago. And NASA has the Perseverance rover on the way to Mars for a sample return mission of its own. There's so many samples coming back to Earth from across the solar system. In your field of Earth sciences, what does that mean for you?
It's definitely a really exciting time to be alive. I guess it's worth remembering that we have had naturally occurring sample return missions from many of these bodies in the past, including the rocky planets of the inner solar system and asteroids, come to us in the form of meteorites. We're fairly sure we know where they're coming from, but to be able to go and get pristine samples ourselves really helps us peg our observations and test the hypotheses we've had for decades.
Now, can you tell us a little bit about the SAMI Galaxy Survey? It started 7 years ago. What was the genesis of the idea?
Yeah, so actually it started back in 2013. And I guess the genesis of the idea is that we really wanted to understand why galaxies look the way they do. It seems like a pretty simple question, but actually it's really hard to answer. And so we had a number of ideas about how what galaxies look like. For example, we've all seen images of galaxies from the Hubble Space Telescope and other telescopes like that. And they all seem to appear pretty diverse. So we see a number of different shapes of galaxies. They have a number of different colors. So they can be blue or red. When we see very blue galaxies, that means they're actively forming new stars, for example. Or if we see very red galaxies, that means they haven't formed stars generally for a few billion years or so. So there's a diversity of characteristics that galaxies have, and our survey was all about trying to disentangle what causes that diversity. So in order to do that, we needed to use about 250 nights on the telescope with an instrument called SAMI, the Sydney AAO Multi-Integral Field Spectrograph. We like our acronyms in astronomy, as you might be fully aware.
Yep.
So SAMI it allows us to take what's called integral field spectroscopy. Now, integral field spectroscopy is essentially we take an image of a galaxy, but for each point in the galaxy, we have a spectrum. So a spectrum, you might be aware, is where we break the components of the light up into its different wavelengths, much like a rainbow breaks up the light from the sun into its different colours, but much more granular. And so that allows us to make many different measurements of galaxies and try and disentangle the diversity of the galaxies.
Dr. Mccamish, thanks for a little bit of your time.
No worries. Thank you for inviting me.
Now, can you tell us what is phosphine?
So phosphine is a molecule that has a phosphorus atom linked with 3 hydrogen atoms. So it's one of the simplest phosphorus-containing molecules out there.
And that key building block was recently found when scientists were poring over the 1978 Pioneer mission data to Venus. Why was that announcement so controversial?
So I think they went back and found the data in 1978. The recent data was they found some spectral lines using microwave spectroscopy, looked in the atmosphere of Venus, and the reason it was so controversial is because phosphine just shouldn't exist in Venus's atmosphere without something weird going on. So it should be destroyed by the sulfuric acid, and we don't actually know how it's produced in the first place. So you might have heard the stories about maybe it's life.
Bobby, you're the Deputy Director and General Manager for Science and Learning at Questacon, so you're in the best position to tell us about the centre and what it aims to achieve.
So Questacon, many generations of Australian school kids have been there. It's a typical journey that years 5 and 6 take from schools right across the country. They come to Canberra, they visit the national institutions, and the treat at the end of their big trip is often a visit to Questacon, which is a hands-on science centre with over 250 experiences and lots of really great and amazing experiences and staff here to help you. But beyond the National Science and Technology Centre in Canberra, we also have a National Technology Learning Centre, also here in Canberra, that reaches out across the country. And we take exhibitions, shows, workshops, dialogue and experiences out to schools and communities, large and small. Wherever you are, Questacon will be coming to you at some point.
Richard, we know that Tidbinbilla is a critical link for NASA's Deep Space Communication Network, providing one of 3 up and downlink facilities for spacecraft. But can you tell us about your specific role?
I'm part of the operations team in Canberra. I'm one of the operations team leaders. And essentially we have a crew of 16. And for daylight hours, currently that's 8 till 5, we'll control not only the Canberra assets, but also the assets in Madrid and Goldstone, the other 2 NASA DSN sites.
With so many missions currently out in the solar system and beyond, do you have a favourite spacecraft to talk to?
You have the nostalgic spacecraft and you have the exciting spacecraft. It's like going into a pub and picking out a particular person you want to talk to. If you look at the Voyagers, obviously we talk to Voyager 1, only Canberra can talk to Voyager 2 now, 22 billion kilometres away. That I've been in Canberra operations now for 32 years. And when I started, so Voyager 2 was just going through its Neptune encounter and now in interstellar space. So it's a spacecraft that I've spent my entire career tracking and hopefully probably until I retire. But then you have the other spacecraft like Parker Solar Probe, and which is a far more dynamic mission, I suppose. So getting so close to the sun and then sort of zooming out to almost the point of the orbit of Venus before flying back in again. So Voyager 2 will probably always be my favorite, but there's always something new, the tracking of MSL, to Mars, was incredible. So all the rovers around Mars are incredible, and we do those as well. And I should point out that it's not only the NASA spacecraft that we support, but it's also other agency spacecraft as well. We are tracking a lot of ESA spacecraft. CSIRO does manage the ESA site in New Norcia as well, and they have a single antenna. And we have a 70-meter and 3-beam waveguides, and we complement each other. So we are supporting a lot of ESA spacecraft because their network has almost hit saturation point, I think, especially with the Mars missions. But we also do the JAXAs, Arab Emirates is a new one, the Indian Space Agency as well. So, up till probably 6 months ago, we had mid-30s supports, but with Artemis being launched in November, hopefully, carrying 13 CubeSats, that's made life a little bit more interesting for us because now we're suddenly having these huge influx of the smaller spacecraft, which we still have to treat as the same as any flagship.
Well, Professor, what goes in must come out, but it turns out in the case of your research, we have clean elements becoming dirty ones. How does that work and what does it mean?
Well, the way it works is that, so it starts very early in the formation of the universe. The universe made a very clean system, mostly hydrogen and helium. And then over the course, stars started to form. And when a star forms, it turns that hydrogen and helium into heavier elements, carbon, nitrogen, oxygen, all the way up to iron, and everything that you're made of, everything that you see around you came from a star. And so that's what we astronomers call polluting the cosmos. And that happens in galaxies where you have this clean gas from the universe, initially from the Big Bang, accreting, falling onto galaxies. And then galaxies, they swirl it around and crunch it into stars. And then a few million years later, those stars explode and they shoot the gas back out of the top of the galaxy in polluting the cosmos even more. And so it's a constant cycle. And what it means is it means that galaxies refresh themselves, and over time they change the universe around them. They're not isolated, they're connected to the part of the universe that they live in.
Well, when we say exhaust, I think of what comes out of the tailpipe of a car. Is what we have here as toxic as that on a universal scale?
Not at all. It's quite the opposite. So everything that you see is that exhaust. So what comes out of the tailpipe of a car is quite bad for you. But part of the exhaust from a star exploding is the atoms that make you up, that made up the planets that we live on. And so even though it's polluting in terms of what an astronomer says, it's actually quite necessary and useful for promoting life and eventually creating new planets around new stars in other galaxies.
Now tell us a little bit about this carbonaceous chondrite meteorite that was discovered. I understand that it's a pretty rare finding.
Yeah, so we had a carbonaceous chondrite fall on the 28th of February this year. It fell around 9:54, and it went basically splat into someone's driveway, made a little dent, and shattered into a million pieces.
Wow.
So yeah, it's a carbonaceous chondrite. It looks like it's a type of carbonaceous chondrite called a CM chondrite. And it's the first time anything like that has fallen on the UK ever. So it's possibly the most significant thing to happen to UK planetary science in history, which is awesome. And yeah, like you said, it was seen by a load of camera networks, including the sort of Desert Fireball Network expansion as part of the Global Fireball Observatory out at Curtin University, which sort of myself and Sarah McMullen at Imperial College London have been organising. So we saw this thing fall along with all the other camera networks that work in the UK. Our friends over in Curtin University told us where it would be, and then we went out looking for it. And yeah, the result is this really precious space rock.
Ben, you and colleagues from the Netherlands have used their national observatory, Astron, to search for exoplanets, and it seems as though 19 red dwarfs are telling you a little more about themselves than expected.
Yes, no, we're super excited. So we used the world's most powerful radio telescope, LOFAR, to search the whole sky, or at least a large section of the sky, for radio waves from M-dwarf stars, that is red dwarf stars, the smallest kind of star. And quite unexpectedly, we found many radio bright, but circularly polarized, that is you pick them up with a circular antenna, radio sources. Now what's quite exciting is this is exactly what Jupiter looks like if you look at it with radio glasses on. So radio telescopes looking at Jupiter see circularly polarized radiation from its interaction with its moon Io. Io is whipping around in Jupiter's magnetic field, and it's driving this powerful aurora that you see with optical light, but you also see powerful radio waves. And so we think what we're seeing is a scaled up version of the Jupiter-Io interaction around these other stars.
My most humblest of thanks to each and every guest who beamed in across the year to discuss their research, the latest piece of news, or even just as a subject matter expert. It's been a real thrill to get to know so many people doing so much amazing work, and I cannot wait for 2022's season of Talkin Science interviews. This countdown is by no means, of course, all that we've done this year, so catch the Talkin Science interviews playlist to watch them all. And I'll see you for another edition real soon.